Lesson 5, normal distributions and the empirical rule. Symmetric probability distributions are often defined as normal. Remember, and we referred to this already, but if something is symmetrical, then it matches left side to right side. So if you fold it in half, everything would line up, everything would match. That's called a normal distribution because it's symmetrical. Remember, standard deviation is how far you are from the mean, the average. Now, all normal curves have the following properties. And they're sometimes called, whoops, they're not called whoops. They're called 68, 95, 99.7 rule. And that's because if you look here at this normal distribution, you can see that if you drew a line straight down the middle and folded it in half, it would match up. That's symmetrical. Now, what they're talking about here in this part is, here's your mean right here. And these are +1, +2, +3 standard deviation. That symbol here, remember, that funky little symbol means standard deviation. So 68% of the data will fall between +1 and -1. 95% will be between +2 and -2, and 99.7 will fall between +3 and -3. Now if you split that up, divide by 2, it breaks down like this. 68 divided by 2 is 34, 34. And then the next section is 13.5, 13.5, 2.35, and 0.15. And again, that is just the one left divided by 2. So it says adult women in the U.S. have an average height of 65. Well, that means we're going to put 65 right here. With a standard deviation of 3.5 inches. That means we're going to add 3.5, and then add 3.5 again, and then add 3.5 again. On the left side, we're going to subtract 3.5, and we're going to subtract it again, and we're going to subtract it again. %68% of the women, well, remember, that's from here to here, +1 and -1 standard deviations. So 68% of the women are between 61.5 and 68.5. %16% are shorter than what? Okay, well, let's look at this. 16%, remember, we have 0.15 here, 2.5 here, no, sorry, 2.35, and 13.5 here. If you add all those up, you get 16%. So from here to here is 16%. In other words, 16% of the women are shorter than 61.5. 95%. Well, if you look back up at the chart, 95 is between -2 and +2. So that means they're between 58 and 72 inches. All you're doing is just reading a chart, basically, at this point. 2.5% are taller than. Well, remember, we have 0.15 here and 2.35 here. If you add those two together, you get 2.5. So therefore, you're talking about taller than 72 inches. Now, it says if 500 women were randomly measured, how many would you expect to have a height less than 61.5? Well, that's 16, it just says right here, 16% of women are shorter than 61.5, so we're going to take 500 times 0.16. So we would expect about 80 women out of 500. All right, as usual, if you need to pause or go back or anything, please do. College entrance exam design scores are normally distributed with a mean of 500 and a standard deviation of 100. So that's easy. That's 600, 700, 800, 400, 300, 200. So what percentage is between 400 and 600? Between here and here. Plus and minus 1. We look back at our chart on the first page, that's 68%. What's the probability a randomly selected test score is above 600? Well, that's again our 2.35, sorry, 13.5, I put in the wrong section. So let's move this, nope. Let's move this there, you go away. This is 13.5, and this is 0.15. If we're looking for greater than 600, we add those numbers up, and that's 16%. Now, you're starting to get used to these numbers, 2.5, 16, and so forth, as you use them more often. Those kind of pop into your head. What's the probability a random selected score is less than 300 or greater than 700? So less than 300 is 2.35, 0.15. Okay? And that, as we said before, is 2.5. So you have a 2.5% chance to be less than 300. Greater than 700, well, that's right here again, another 2.5%. So that's a 5% chance to be one or the other, less than 300 or greater than 700. If 1,000 students took the exam, how many would you expect to have a score greater than 400? Okay, well, greater than 400, remember, greater. So this is 34. From here on out is 50%. So 84% of the population should be above 400. So 400 people times 0.84 is 336 students. So you're expecting most of them to do better than 400. Now, the standard curve is a normal curve with a mean of 0 and a standard deviation of 1. Plus 1, plus 2, plus 3, minus 1, minus 2, minus 3. A data value x from a normal distribution with a mean of, that's our symbol for it, and our standard deviation, there's our symbol for it, can be standardized by finding the z-score. Okay? And anything above 2 or less than 2 is negative 2 is considered unusual. It's outside the norm. Now, technically, 1, when we say plus 1, 1 is a z-score. Plus 2 is a z-score. Plus 3 is a z-score. But there's all the numbers in between and above. So here's what the formula is. It's x minus our funky u over that. So let's put it in real terms. It's our actual score or value minus the mean over the standard deviation. Very simple. So remember, adult women have an average height of 65 with standard deviation of 3.5. If you had a woman who was 68.5 inches tall, now let's go back and look. Please stay with me on this one. 68.5. Where is that? It's, whoops. Love when it does that. It's right here. You already can see what the standard deviation, what the z-score is. It's right here. It's 1. I just said those numbers are z-scores. So let's see mathematically why that is. If we do 68.5, the actual score, the actual value, minus the mean, divided by the standard deviation, we end up with 1. So now we're going to find the in-between. So let's go back to our graph real quick. 63.7. We're not going to do it for all of them, but 63.7, where would that be? It's a good idea to get an estimate. So 63.7 would be somewhere in there, between 61.5 and 65. In other words, we should get a value between 0 and negative 1. It's kind of a nice idea to predict, looking at the graph, what the number should be. So if you do something wrong on the calculator, it doesn't make sense and you can go back and correct it. So 63.7, actual score, minus the mean, divided by standard deviation. And when you type that in the calculator, you get negative 0.37. And that makes sense, between 0 and negative 1. Okay, 66 inches tall. If you look back at your graph, okay, that's above 65, but less than 68.5. So we should expect our answer to be somewhere between 0 and 1. 66 minus 65 divided by 3.5. And we get 0.29. Makes sense. 62, where would that be? Well, again, if you look, 62 would be really close to negative 1. Right about there. So we expect it to be, maybe 0.8, 0.9, something like that. Let's see what it actually is when we calculate it. 62, oh, why it does that? 62 minus 65 over 3.5. And we get negative 0.86. Pretty close to negative 0.9. So our estimate makes sense. Now Donna belongs to the Beanstalk Club. She's very tall, Dana. Her z-score is 3.4. How tall is she? Well, now we're working backwards because we know her z-score is 3.4. We don't know her actual height. We do know the the mean, and we know the standard deviation. So now we just work backward algebraically. We're going to multiply both sides by 3.5. Okay? And that gives us 11.9 equals x minus 65, because these cancel. And then we add 65 to both sides, and we find out that she's 76.9 inches. And again, let's just look real quickly. Where is that? 76.9 inches? Well, our last standard deviation of 3 is 75.5, so she's somewhere out here. And if this is plus 3, 3.4, that makes sense. So I hope you're seeing the connection between the z-score and the location on the graph. Okay, last but not least, almost done. Jill scored 680 on the math part of the SAT. Distribution is a mean of 500 and deviation of 100. Jack took the ACTs and got 27. The mean on that's 18 and standard deviation 6. Who did better? Okay, well, that means we got to do two tests. We got to do Jill with her SAT. Now we got to do Jack with the ACT. So her score was 680, the mean was 500, and the standard deviation was 100. For Jack, his score was 27, the mean was 18, standard deviation was 6. Let's see what they got. Well, Jill got a 1.8, and Jack got a 1.5. So who did better? Jill did. Because if you look at the normal distribution real quickly, something like that, here's 0, here's plus 1, here's plus 2, we got 1.5, and we have 1.8. Obviously better. And that's it.